Okay, so New York style in Python. Like I can, I can read the content image, like the style image, the content image, this style image. The preprocessing, like we just manage the make it to 0 and 1, like minus the min and make divided by the standard deviation, like this a pretty normal preprocessing and post-processing. So here's the thing. We are using the Pretrend VGG 19 to the base network. So we know that the VGG have like 5 blocks. So the style layer is kind of the first layer for each block. And we have 5 blocks. I pick up the first layer for each block and get to match the 4 styles here. The content which we just pick up the kind of the last block. I think it's the 4th block, but the last layer, kind of the 25, sit between 90 and 28. Okay, so then we just get this as pre-trained weight. We don't need, because this we don't want. Here we don't need to train the network, just for feature instructions. So for feature instruction, what do we do here? Given the x, given the number of layers, the content layers, number of style layers, we just run layer by layer and get the output and just put into the list of ND arrays. So this is the style. So given x, for each layer, we just evaluate one by one. If it's on style layers, we just put into styles. If it's on content layers, we just put in the content, return it. Basically, we can, given x, we can feature instructions. Okay, so, well, like, I gonna get the contents. I give a content image, I pre-process it, and get the features, this content features, and also give style image. Given the style image, I pre-process the style image, and I also get the style features we have. Like we return the style and x and the y. Okay. The loss function for content, we just L2 long for the loss function, minus square and do min. For the style loss, what do we do here? So given x, this is the number of channels we have, and n is kind of the rest of it. The batch size is always equal to 1. So n is just the width times the height, the number of pixels you have. So then we reshape it to number of channels and the width times height. So this is the number of variables we have, and n is like the n samples from each variable. So for gram matrix, we just do x times x dot, x transpose, and do the thing. So we have covariance matrix for this random, kind of random matrix here. So we assume the mean is 0. So we just, this one kind of like the second order statistics for this random matrix. Then the style loss, given the y hat, assume this already have the gram matrix, just minus the L2 long between the gram matrix of the 2 input. So this is style loss. Okay. The TV loss is like, it's just easy. I just, every time 1 minus the 1 row down and 1 column left and do the absolute value and do the min. So that's the TV loss. So now we have 3 loss. We need to have weight. Kind of, this is the content weight, style weight, and TV loss weight. And we do a little bit normalize. So this is like, skip this function. Like, I just given 3 loss, given different weight, I just combine all this loss together, return 1. Similar thing we did at the SSD before. So at the last, you need to generate the image. You can do from random, but well, you can. So give an image because. So here, the only difference here is that, like before we learned the parameter for the network. Now here, differently, we need to learn the gradient of the input image because we need to update the input image for random, maybe from the initial point to the learned image at the end. So here we put into a block and make the weight is basically the image we have so that we're going to compute the gradients of this input image. So for the fourth function, you just do nothing, just return the image. So, but we need to get the gradient of the image. So the init function, init other things, I can skip. So here for training. What do we do for training? So firstly, so X is the learned image, the thing we're trying to learn. So firstly, we get the style, the content features, the style features, and then given these features, we compute the loss according to the style image and the content image. Then we run the backward function. So the only thing here, the trainer, let me see the trainer. The trainer, this is the input image. The parameter is itself. Like the trainer need to update the learned image here. So this is the only difference. But the other things, similar to like SSE, we have compute a bunch of loss, compute a bunch of output, and compute the loss functions we have. The only thing we will print something. And then I quickly show the image here. One trick here, you first train a small image. Like you train a small, like 300 by 200 image. You can see that there's a content loss, style loss, and the noise loss. You can everyone decrease by a little bit. Finally, this kind of the learned image, like 300 by 200. And then, but usually if the image is too small, like you lose a lot of local information there. So it's pretty blurry here. Then what you can do, you can train a bit larger image. Like you can do 1020 by 800. The trick here that you can choose the learned image from the small size as the input, as the initialization of the larger one. You just resize to a larger one to make it the starting point. So then you can make the training much faster. Okay, so this is kind of, well, you learned a little bit larger one. But still a little bit blur that because this is still too small. If you really want to do good, like, this is kind of like, if you have a lot of memory, you can do a very large scale. Like this is 8,000 times 8,000 almost like. So you can see if you give a very large ones, you can learn things a lot. Let me show you the original image. So this is the learned one. And this is the original one. The original one is a picture took from Renton Mountain Rainier at Seattle. And this is kind of the style image. You can see that this is the learned one. Kind of keep some style from the style image. But usually you can, if you want to have fun, you can change the content image, change the style image, and try two different combinations. So that's it.